Hello, welcome to this video 6-8, and we are going to talk about anti-differentiation. Now, our learning intention is to learn anti-differentiation rules so that we can integrate functions represented symbolically or algebraically. Now, up until now, we have spent a lot of our year and time looking at derivatives and applying derivative rules. Now what we're going to do, and what we've been doing, is we will transfer our focus to integrals. And these are also known as antiderivatives. Antiderivatives. Now remember, derivatives and antiderivatives are inverse operations. So they undo each other, and we would expect to see that these ideas are connected and that they have a relationship when we do this. Okay, so what we're going to go ahead and do is look at some of the following examples, and they say, given the following functions, find f prime of x. So we're going to exercise our derivative muscles first before looking at antiderivatives. So if I have f of x equals x squared, f prime of x is just going to be equal to 2x. That's the simple power rule. F of x is equal to sine of x. Well, then f prime of x, derivative of sine, is cosine of x. And number 3, if f of x is 3, well, the derivative of a constant, we know, is 0. So now what we're going to do is we're going to think about this in reverse. What if I had a derivative function, g prime of x is equal to 2x? What do you think would be the equation for g of x? And I know you're thinking, Schwarberg, it's right above. G of x would be equal to x squared. And that's because we have to undo that differentiation, right? That 2 came from the power. We can move it back into the power and remove that coefficient. Okay, so let's use this understanding and kind of a trial and error on a few of these here. So I have example number 1, and it says, given h prime below, use your understanding of derivatives to find h of x. Okay, A, if h prime of x is equal to cosine of x, well, I know that in order to get cosine of x, that's the derivative of sine. So h of x must be sine of x. B, h prime of x is equal to negative 2. Okay, well, in order to get a constant as an answer from a derivative, I know that that must be the coefficient of a linear function. H of x equals negative 2x. That's our actual function, right? Because when I differentiate, that power of 1 disappears, and we just have that coefficient, negative 2. C, h prime of x equals 3x squared. Okay, well, h of x is equal to, remember that coefficient came from the power, so what if I turn that power into a power of 3? If I differentiate that, do I get 3x squared? And the answer is yes. Okay, and then D, h prime of x equals 0. How do you get nothing from taking a derivative? Well, h of x could be some number. It could be, some of our favorite numbers. 4. It could be 7. It could be anything. It could be what we call a k or a c value of a constant, right? And if I take the derivative of that, that gives me 0. Okay, E, h prime of x equals negative sine x. Man, these are getting a little bit more tricky, but I know that sine and cosine are related, so the derivative of cosine of x, doesn't that give me negative sine x? Yes, it does. Okay, and then F, h prime of x is equal to 4x squared. Well, h of x, I know when I take a derivative, the power decreases by 1, so I know I have to have a power of 3, and notice that that 3 disappears. So what if I leave a coefficient of 4 and I have a denominator of 3? When I go ahead and multiply that, those will cancel out. So hopefully you were able to kind of think about these and see some of these connections. If I differentiate these functions, do I end up with these functions above? So we're going to go ahead and talk about antidifferentiation or integration. And notice these terms are used interchangeably. They are synonyms. And here are just some of the must-know basic integration rules for functions. So the integral of sine of u du, and we're just using u as our variable here, that is going to be equal to negative cosine of u. And what I'm going to do too is I'm going to add what we call a c value, or I'm going to add a constant, because if I differentiate that function, what happens to that c value, that constant value? Well, we just learned that that turns into 0, turns into nothing, it disappears. So I could have some constant value added on. We don't know, and I'll show you this clearly through examples. Number 2, the integral of cosine of u du is equal to sine of u plus c, some constant. Number 3, my favorite, the integral of e to the u du. Well, what's the derivative of e to the u? E to the u. What's the integral of e to the u? E to the u. This is the total Spider-Man meme in mathematical application. So e to the u plus c. All right, number 4, the integral of u to the power of n du, where n cannot equal -1. Okay, so that's just some power, and this is what we call the power rule for integration. I'm going to have my function, whatever that is, that's going to stay the same, and the power is going to increase by 1. Notice that I did that up here for all of these functions. When I went from x squared, I went to x cubed. Differentiation makes the power go down. Integration makes the power go up, right? So x squared gave me x cubed. Notice I had 0 here, that gave me a constant, and we'll look at some polynomial examples here in a bit. But then too, I have to do something with the power. I have to divide by this new power of n plus 1, okay? And that's because differentiation multiplies. Don't I bring down this power, right? This n plus 1, I'm going to bring it down in front and multiply. Well, integration is the inverse. That is the inverse of multiplication, division. So u to the power of n plus 1 divided by n plus 1 plus c, plus some constant. Number 4, the power rule, that's going to be your bread and butter, just like when we're differentiating. And I'll show you more examples in a bit. And then lastly, number 5. Number 5, the integral of u to the power of -1 du, also viewed as the integral of 1 over u du. This is equal to the natural log of the absolute value of u plus c. And I know that seems like an odd one, and you're like, hey, why don't you just apply the power rule to this? Well, if I apply the power rule, if I add 1 to -1, that's the power of 0, and then I divide by the power of 0, and I'm dividing by the power of 0, and I don't have those godlike powers. You cannot do that. So u to the power of -1, that has its own special rule. It's 1 over u. That's the natural log of the absolute value of u plus c. Okay? So note, all of these formulas are in terms of u, and this will lead later to what we call u substitution. We'll talk about this at the end of the unit, u substitution. And this is just integration's equivalent to the chain rule. So it's the same idea that we have to account for the chain with derivatives. We need to do this with integration as well. And we'll dedicate several days just to that idea. Okay, So before we go ahead and begin, just a couple of important tips for integration. And we had these same ideas for differentiation as well. What we're going to do is we're going to turn all radicals into powers. So if it's a square root, I'm going to turn it into a power of 1/2, okay? And then number 2, no variables in the denominator. We're going to use power rule for all of those, and that just requires adding 1. And just moving it up will make this process nice and clean and easy for us, okay? So, all right, let's go ahead and look at some of these examples. And these first ones in example 2 deal nicely with the power rule here. So I have the integral of 5x cubed dx. What is this equal to? Well, I'm going to go ahead, I'm going to add 1 to the power. This is x to the power of 4. And I'm going to divide by that new power. So 5x to the power 4th divided by 4. And I'm going to add a constant. Do not forget your plus c. So I have 5/4 x to the 4th plus c. That's a constant value. Okay. B, the integral of 2/3 x squared dx. Don't be scared by them writing this fraction off to the side. That throws off a lot of my students. Notice that you could easily write this monomial term as 2x squared divided by 3. It's the same idea. So I'm going to go ahead and I'm going to add 1 to the power, so 2x cubed, okay, over 3, and I am going to divide. I'm going to divide by 3. Divide by 3. I'm going to add a constant here. Now, what ends up happening with this 3, remember, when you're dividing fractions, what ends up happening is you multiply by the reciprocal. Multiply by the reciprocal. So what you have here is you have 2/3 x cubed times 1/3, right? Isn't the denominator of this 3 1? So when you add that power 3 into the denominator, usually it adds right here. So I can expect that denominator power to go to 9. So I have 2/9 x cubed plus a constant there, okay? All right, C. I have 4x to the 5th over 3 dx, okay? I'm going to increase my power by 1, so 4x to the power of 6. And I'm going to have 3 times 6 in the denominator plus a constant. So this gives us 4/18 x to the power of 6 plus c. And we'll go ahead and reduce that. So 2/9 x to the power of 6 plus c. Okay, that is the basics of the power rule. Increase the power by 1 and divide by your new power. All right, let's go ahead and look at some kind of quirky, unique integration examples, but these are just as important here. I want to integrate 3 to the power of dx. So notice this is just a constant, and a constant has a power of 0. Constant has a power of 0, right? This is actually like an x to the power of 0 term. So when I integrate, this is going to be 3x plus some constant. And just think about this in reverse. If I was to differentiate 3x, wouldn't that just give me 3? So I'm integrating, my power goes up to 1. I'm dividing by 1, right? We have 3x plus c. E, integrating, and it looks like there's nothing there with respect to y. Well, there is something there. It's an invisible 1. It's an invisible 1. So this integral is just going to be y. Notice I have to pay attention to what they're telling you to integrate with respect to. I'm integrating with respect to y plus some constant. Okay? All right. F. Here I have the integral of x cubed minus 4x plus 1 dx. And this brings us to a property. If I'm going to integrate this whole entire thing, I want to break it up, and I want to do it separately. I'm going to take the integral of each component. So the integral of x cubed dx plus, actually I guess minus the integral of 4x dx plus the integral of 1 dx. So I can take the integral of each piece, and this is a property that we'll formally define later. So this gives me x to the 4th divided by 4 minus 4x squared divided by 2 plus x plus some constant, right? This is what we call an indefinite integral. I'm going to add that constant because I don't know, what number could have been added there. So I'll clean this up. 1/4 x to the 4th minus 2x squared plus x plus c. All right. Couple another rounds of integration. We have here now the radicals. I'm going to show you the radicals, and what I want you to do, this comes back to that first step. Just go ahead and rewrite this. This is 5x to the power of 1/2 dx, and when I integrate this, this is just going to be 5x to the power of 3/2, and I'm going to divide by 3/2. And again, we can generalize a process for this. When I divide by a fraction, I end up multiplying by the reciprocal of the denominator. So this ends up becoming 2/3 times 5x to the power of 3/2 plus c. Okay, so we have 10/3 x to the power of 3/2 plus a constant. Whew! I know you guys love fractions. Okay, let's look at another one. B, we have the integral of 2 cubic root of x dx. Okay, I'm going to go ahead and rewrite this first. So this is the integral of 2x to the power of 1/3 dx, which ends up giving me 2x to the power of 4/3. And I'm going to divide by 4/3, which is end up multiplying by 3/4. So we end up getting 6x to the power of 4/3 divided by 4 plus a constant, which is 3/2 x to the power of 4/3 after reducing that coefficient. Okay, and here is C. Go ahead, try this out. Now I've shown you lots of examples. Try this example, and then I'll show you the answer here in a second. Okay, here is the solution. The first thing that you should have done is rewrite this as x to the power of 1/4. And when you integrate, you're going to raise the power by 1. So if I'm adding 1 to 1/4, that's 4/4, right? Isn't it the same as 4/4? So that's x to the power of 5/4. Okay, 2/5, and I'm going to divide by my new power of 5/4, which is multiplying by 4/5, and I'm going to have a constant here. So we should have gotten 8/25 x to the power of 5/4 plus a constant. Okay, did you get it? Good, good. Okay. All right, let's go ahead. Let's look at example A. All right, example A, hopefully this structure you recognize as the natural log. So if I integrate 1 over x, shortly this is going to be the absolute value, the natural log of the absolute value of x plus a constant. That's what it is. Now, what I advise that you do is you go ahead and you write this as a negative exponent, the integral of x to the power of -1 dx, because we're going to utilize that strategy going forward for everything. People see this and they just automatically slap everything into a natural log, and they're like, that's the antidifferentiation rule. Well, no, it only works if your power is -1. Okay, and why this is, again, not power rule, right? I can't have x to the power of 0 and then divide by that new power of 0. So that doesn't work. This is the natural log of the absolute value of x. This is one of our key integration strategies. Okay, so B. Let's go ahead and start applying this. We have 2 over 3x squared. Okay, so what I'm going to do first is I'm going to rewrite this. This is the integral of 2x to the power of negative 2 over 3 dx. Okay, I just moved up the power with the negative exponent property, and now I'm going to go ahead and integrate. So my power increases by 1. I have 2/3 x. I'm going to add 1, so be careful. Negative 2 plus 1 is negative 1. Okay, and I'm going to divide by negative 1, so I can add a negative, and then I'm going to add a constant. Okay, so that's good. If you're going to compute or calculate with this, you may see it in this form, plus c. That's just putting that negative exponent property back to use and moving it down into the denominator. All right, c. Here is c. Again, I'm going to go ahead and integrate. I'm going to, well, the first thing I want to do is I'm going to move out that negative. I have the negative integral of 9/5, and I'm going to move up my exponent, x to the power of -4 dx. Okay, so this ends up being negative 9/5 x to the power of -3, okay, and I'm going to divide by -3. I'm going to divide by -3, which we know is the same thing. I left myself enough room as multiplying by a -1/3. Okay, so plus a constant. Don't forget your plus c. So this ends up giving us, we have the two negatives that cancel. Sorry, my notation was a little weird. I was even second guessing myself. I'm like, wait, why am I writing it like this? So -3 we have, I'll reduce after. So 9 over 15 x to the power -3 plus c, which reducing by 3, we get 3/5 x to the power 3 plus c. Okay. At this stage, you may have questions like, do I have to reduce? Do I have to move the exponents back into the denominator if they're negative? Do they have to be positive? Can I leave them negative? And my answer is kind of the same as it's always been. If it's a free response question and that's what you're doing, that's fine. If it's a multiple choice, you may have to manipulate it algebraically to find that correct answer. And then generally, if you're going to do calculations, you want your exponents to be positive. So we'll get to utilizing these integrals in the next lesson. Okay, example 5. All right. So now we have both of these factors in play here. I'm going to go ahead. I'm going to rewrite this. This is the integral of 2 to the power of. Notice this is x to the power 1/2, and it's in the denominator. So I'm going to bring it up. X to the power of -1/2. dx. Okay, so there's rewriting my radical as a power and moving it into the numerator. So I'm going to go ahead and integrate this. This is 2x to the power of, I'm going to add 1. This will give me a positive 1/2, right? Adding 1, that's 2 over 2. Okay, and then I'm going to divide by my new power, which is 1/2. Okay, divide, well, I guess I'll write it like this. Okay, plus c, which ends up just multiplying. It's 2 times 2x to the power of 1/2 plus c. Okay, so we get 4x to the power of 1/2 plus a constant. All right, b, the integral of 3 over 2 cubic root of x dx. Okay, so let's go ahead and rewrite this as 3/2 x to the power of -1/3 dx. And I'm going to integrate, so this is just a power rule. I'm going to add 1 to this, which is 3 over 3. So we have 3/2 x to the power of 2/3. And I'm going to divide by 2/3, which ends up being multiplying by the reciprocal, which is 3/2. So that's the way I like to do it. Rather than dividing by a fraction, I just multiply by the reciprocal outright. And that seems to be cleaner than doing kind of this step over here. So we have 9/4 x to the power of 2/3 plus a constant. All right, C. I'm going to let you go ahead and try this one. Please pause the video. Utilize this as a knowledge check to see if you understand what is going on. All right, here is the solution. This you can rewrite as the negative x to the power of 1/5 over 3 dx. And we're going to go ahead and integrate. And I'm going to add 1. So we have negative x to the power of 4/5 divided by 3. And I'm going to multiply by the reciprocal, or I'm going to divide by my new power, which is 4/5, multiplying by 5/4, plus a constant. Did you add the plus c? Make sure you add the plus c. Very, very important. Okay, so we have negative 5x to the power of 4/5 over 12 plus some constant. And again, just for kicks and giggles, so I'm going to add a negative 5/12, and I'm going to make this the 5th root of x to the power of 4. Just put that back in radical notation just to see if you're familiar with that. Okay? All right. I have one last example for us, and it's just dealing with everyone's favorite thing in the world. That is trig. And we're going to split this lesson. We'll finish this up on the next day because it's pretty long. Example number 6. Let's go ahead and integrate the sine of x dx. Now, I didn't talk about this above, but again, I want to recall your memory to this little chart that I went ahead and drew when we started differentiating trig. So I just drew kind of like the unit circle, and I said, hey, where are these values? 1. So sine of x is 1 at the North Pole. Cosine of x is here at angle 0 or 2 pi. And then over at pi, we have negative cosine of x, -1. And if we differentiate, you get this idea. So d dx gives us this answer, and it works clockwise, right? If I just keep going this way, if I differentiate these, we get the next one. Well, it also works in reverse. It also works in reverse. So if I'm integrating sine of x, I get negative cosine of x plus c. Whoa! Isn't trig awesome? Like, all the unit circle answers are just on your hand if you know the left-hand trick. And then that little diagram right there helps you out with all of these. So using that, let's go ahead and look at B, the integral of negative cosine of x dx. Well, we know that that's going to be negative sine of x dx, using that little cheat sheet. So I know that it's going to be this, sine of x plus c. Now, another way that we can do this is I can take out that negative, and I have negative integral of cosine of x dx. Don't forget that you can pull out the negatives. So again, how do you get cosine? What's the antiderivative of cosine of x? Well, that was sine of x. Okay, so giving us the same answer that we had here. So negative sine of x plus c. Okay, and C. I'll have you go ahead, try this one. Let's see if you got it. All right, hopefully you tried this one. Here is the solution. What I'm going to do is I'm going to pull out that -4 as the multiplier in the front. And I have -4 times the integral of sine of x dx. And this just gives me -4 times the integral of sine of x is a negative cosine of x. Don't forget that negative, okay, plus some constant. And I have a +4 cosine of x plus a constant. And if you don't believe me, just go ahead and differentiate it. If I differentiate this, what do I get? Actually, Well, yeah, you do get that, but mainly that there. Okay, that's going to do it for this video. This was part 1 on basic anti-differentiation. In the next video, we'll go ahead and we'll cover important properties of integration. And again, just something you can do, make flashcards, memorize these. These 5, extremely, extremely important, extremely intuitive. It's just taking the idea of differentiation and working in reverse. Like and subscribe. Catch you in the next video.